take to that. Okay, so now let's try and find one where we do some hypothesis testing. Okay, problem 7 looks like one, right? Okay, management claims that the mean income for all senior assembly line workers, manufacturing MP3 players is $350. A concerned client decides to test that claim for a random sample of 9 employees whose incomes are below. Construct a two-sided hypothesis test for management's claims. In other words, we're not sure if management if their claim of 350, if when we actually sample the population, if we're gonna find that it's lower or higher than 350. So we don't know ahead of time what the outcome here is going to be. And anyway, most of the time we do a two-sided hypothesis anyway, because we are it's a more conservative test. It's harder to reject the null hypothesis that there's no difference between what you measure and what the employer claims in this case, or what he claims the population is that we're comparing it to. Okay, so on our null hypothesis, H null is going to be that the mean salary, that's a mu, mean salary, I'm going to put a space there. So, mean salary is equal to $350. Okay, our alternative hypothesis is that the mean salary is not equal to $350. Okay, so now we're starting off with the null hypothesis. We are going to have to choose. We're going to have to find evidence that makes us 95% certain. They didn't mention here in what level of certainty they wanted, right, or what the alpha was. They should have in this problem. Okay, but if they don't mention it, usually you're dealing with alpha is equal to 5%, or in other words, 0.05. Okay, so that's what is that? Why do we have that 0.05? Well, when we create a confidence interval, we're creating a range that we're 95% sure about. That's the same thing as saying that we think there's 5% chance we could be wrong, that the mean is not in this confidence interval. So alpha and the confidence interval are related. If we have a 99% confidence interval, then alpha is going to be 0.01, 1% chance of being wrong. Okay, so we're going to work with this one and assume that they meant that they wanted to use a 95% confidence interval or 5% chance in alpha, 0.05 of being wrong if you reject the null hypothesis and say that what the employer claims the population mean is, or what we think the population mean is based on our sample, are that far apart. Okay, we only want 5% chance of being wrong if we say that they're different. Okay, so let's go ahead and do this problem. So we would have to calculate the mean, the standard deviation, and the standard error. Okay, so I'm going to do this in SPSS because it's here. I'm only going to do the first part of it, okay, in SPSS because I want to do the second part mathematically. 330, 350, 340, 360, 320, 330, 350, and 340. Okay, that's 8 numbers. I got it right? Okay, so now let's give this a try now. Okay, I'm not going to change the variable name this time. I'm just going to leave it the way it is. Analyze, descriptive statistics. I'm going to go to explore. I'm going to move, notice now we have 2 variables here. I'm going to move this new variable that we created, the salary, in here. Indeed, statistics is still turned on and it's set for 95%. I'm going to, actually, I didn't want to do this. I want to take the extra step. That would answer, that would give us a much more descriptive answer than I wanted to. I'm going to go to, instead of explore, descriptive statistics, so that I could just, I just wanted to do the raw calculations, the beginning calculations for me. And here's our output. Our mean is $340 and our standard deviation is 13. Imagine I could have done that with a calculator or with Excel. 340, and our standard deviation is 13. Okay, so let's go down here, 340 and 13. Let me pull this up. Okay, so X bar is 340, right? And our mean is, that's our mean, X bar is 340, and our standard deviation is equal to, was it 14 or 13? 14, right? Okay, everybody agree with that? So now the sample size was 8. Okay, so now I have to calculate my standard error. My standard error is equal to my standard deviation divided by the square root of the sample size, divided by the square root of 8. Okay, so what's that equal to? My standard deviation is 14. Whoops, let me do this in 2 steps here. Let me clear out my memory. The square root of 8 is 2.82. I'm going to put that into memory and clear this. And my standard deviation was 14. And I'm going to divide that by the square root of 8. And that's equal to 4.95. I'm going to round that to. Again, careful with the rounding. 4.95. It's my standard error. So my 95% confidence interval is going to be, let's see, X bar plus or minus. I'm going to do this in 2 steps. X bar plus or minus. Now I have to decide what that number is going to be, times my standard error, which is 4.95. Okay, what is that number going to be? Well, I need a t-table to decide what that number is. Okay, let me pull up a copy of the t-table. Okay, and for a sample size of 8, we're going to be 7 degrees of freedom, and the column we're going to want to be in is a 95% confidence interval. A tailed probability, right? They say right tail, but if it's a 2-sided test, it's right tail and left tail, right? This is for 2-sided probabilities. Be 0.025 in each side of each side. So this would represent a 5% chance of being wrong, or a 95% confidence interval, same thing. So for 8 degrees of freedom, the number we're going to use is 2.306. So this is going to be 2.306. So now X bar was $340. That was my mean, plus or minus my margin of error. Let's calculate my margin of error. Okay, here's I don't have to round it. I can use that still. I'm not going to round it. Times 2.06. Oops. Oh no. I made a mistake there. 2.306. I have to clear that, unfortunately. Number to recall. Okay, times 4.95 equals 14. So my margin of error is 14. You're right. Degrees of freedom was 7. Did I say 8? Let me go back there. You're right. It was the sample. I was thinking of the other one. Sample size 9. It's n is 8. So the degrees of freedom are 7. So it's 2.365. See how that number gets bigger, and it makes the margin of error wider that you have to add and subtract. So it makes the two numbers further apart. So that was 365. 2.365. Okay, so let's calculate that margin of error again. 2.365 times 4.95 equals 11 point, does that look right? Yeah, 11, that looks right, right? 11.7. Okay, 11.7. Okay, so now if I look for my confidence interval, it's going to be 340 plus or minus 11.7. So at the lower end, oops, at the lower end, I want to keep that. At the lower end, it's going to be 340 minus my margin of error, 11.7, which is equal to 328.30. And at the upper end, it's going to be 340 plus 11.7, which is 351.7. So we're 95% certain that the average wage for this population of workers is between $328 and $351. And our null hypothesis was, where did I put it? Our null hypothesis was that the owner of the factory claims that the average salary is $350. If I'm 95% sure that it's between 328 and 351, can I tell that manufacturer that he's wrong, that it's not 350, and reject that null hypothesis? Can I reject that null hypothesis based on that confidence interval? No, we all agree, right? We can't, because we can't prove that it's different than that amount. We're going to do this a second way, using something called a t-test. What's really happening here is that what we're doing is we're looking at this mean, 340, and we're looking at the mean that the manager claims it would be for the whole population, right? The mean he claims for the whole population is 350. The one that we found in our sample was 340. What we're trying to show is how far apart these two numbers are in terms of standard errors. In other words, if we had sampled from both these populations, how unusual would it be to get numbers that are that far apart? And the way we do that is we actually calculate a real t-value for this exact situation, for this exact distance. The z-score and the t-score, what they have in common is that the z-score and the t-score both represent the number of either standard deviations of the population, in case of z, or standard errors of the samples, in the case of the t-sample. How many standard errors or standard deviation these two numbers are apart. And if they're far enough apart, like in terms of using the z-score, if they're 2.2 standard deviations apart, well, really 1.96 as we know now, standard deviations apart in terms of the z-score. If they're that far apart, we can say that the two means are different from one another. But if they're not that far apart, they're too close together for us to say that they're really from populations that have different means. So doing this t-test we're about to do is the same thing as applying the 95% confidence interval, and is really the same thing in both cases, the z and the t-score, except now we have to calculate what is the z or the t-score. So when we're dealing with samples, we calculate a t-score. So our t-score is going to be equal to, what's it going to be equal to? Well, just like when we calculated z before for populations, it's going to be equal to the x bar value that we want to check minus what we claim the population mean is over the number of over the standard error. So what is this? This is going to be 340 minus 350. Okay, don't get thrown off by its negative number. It doesn't matter. This is turning up on the left side of the distribution instead of where the right, but that doesn't matter. We're just concerned about how far apart they are. Okay, over the standard error. What did we calculate standard error was for this again? The standard error was 4.95, right? 4.95 was the standard error that we count. Here it is. Here's the calculation. That's the standard error that we calculated. 4.95. Okay, so what is our t-score equal to? Our t-score is equal to 10 minus 10 over 4.95, which is equal to, get my calculator out again, which is equal to, let's clear this, and 10 divided by 4.95 is equal to 2.02. 2.02. Well, now I have to say to myself, if we had calculated the z-score, this is more than 1.9 standard deviations apart, these two means, right? So if it were a sample where we knew the population standard deviation, where it was a really large sample and we're using the z-score, would we reject the null hypothesis here? Let me just I'll answer your question in a second, Gene. Let me just get an opinion. If this were a z-score and a big sample, would we reject the null hypothesis here if we got more than 2 standard deviations apart? Yes, we would, because with a z-score, a big population, we only have to exceed 1.96 to say that they're far enough apart. But our problem is that this is a small sample, and we have to exceed the t-score, not the z-score. Now, the t-score isn't the same for all problems. The t-score depends on the sample size. So I'm going to pull up that t-table again. And for a big sample size, like a relatively big sample size like 29, we have to exceed the number 2. Oh, yeah. I didn't remember it was 13 or 14. Yeah, trust me. Yeah. Thank you, Daniela. Assume that it was 14 and instead of 13. Okay. So for a sample size of 30 or 29 degrees of freedom, the number of standard errors apart I would have to be is 2.04. If we're a small sample, like our sample here was, what was our sample again here? Our sample was 8 here. So we're dealing with 7 degrees of freedom. In order for us to say that these two means are far enough apart, our t-score, they have to be 2.365 or more t-scores or standard errors apart in order for me to reject the null hypothesis. And thank you very much. That Daniela pointed out that that I used 13. Excuse me, I used 14 instead of 13 for the standard deviation. So the numbers would come out a little bit differently if you did them, but the operations that you would do would be it would be the same. Okay, so just keep that in mind when you actually, if you go back and do it with 13, you might get slightly different results. So let's see, are we 2.365 standard errors apart? Is our t-score big enough here to say that these two means are really different? I need an opinion. Should we reject the null hypothesis and say that the two means are different? They're far enough apart for me to reject them? No, I can't, because I didn't exceed the value of t that I needed for this sample size, this particular sample size. By the way, this number, this value of t, is called the critical value of t. In other words, that's the value you need to exceed to reject the null hypothesis. Okay, you guys comfortable with that? Does that make sense to you? Yes, good. Okay, let's go over one more example. One more example. Should we do a t-test, a confidence interval, a proportion? Give me a or is there one more in the in this exam, in this sample thing that gave you guys trouble? T-test. Okay, number 6 was number 6 on here. The mayor election. I got one. Can we go over the or? I'm not, Gene. I'm not sure. I'm catching the less than a grade. I gotcha. In other words, the confidence interval. Okay, I'm gonna tell you what. We're gonna do each one of those. We'll do 6. we'll do another t-test, and I'll discuss the idea of single-sided or double-sided tests. Okay, I'm going to start with 6. Let's go over 6 first. Okay, and then we'll do another t-test. Mayoral election is heating up. Christine Quinn is early front runner. Random sample of 400 voters, and there's you got it's called, in computer language, it's called parsing, right? Which means that you're going to go in there and you're going to ferret out the data that you need or the information that you need, or you're going to break it up into sections. I think they use that in grammar too, right? Parsing, they use the term grammar, and parsing in grammar when you locate the noun and the verb and adjectives and stuff like that. So we got to parse out the data that we need. 400 voters, that's our sample size. Found that 230 were likely to vote for Quinn. Oh, okay, so now it's either vote for her or not vote for her, so this is a proportion. 230 out of 400, so 230 over 400 is the proportion we're going to be working with. Conduct a hypothesis test for the probability that she would receive a majority of the mayoral vote. Well, it's a little bit tricky because they didn't actually give you a percentage that you're supposed to compare this to. In other words, 230 out of 400. Okay, Pcap, our sample proportion, is equal to 230 out of 400. Okay, and that's equal to, might as well figure that out right now. That's equal to, clear everything, 230 divided by 400 is equal to 57.5%. 0.05, 0.575. 0.575. Something a little hard. Even with this, I'm going to put this somewhere I can get to it and see it. Okay, even with this graphics tab, it's a little hard to write. I got to mute some more people here. Okay, okay, good. So now let's calculate. Let's figure out what are we comparing this to? The problem said we're asked to determine whether or not she has a majority of the population. This is the proportion of people in the sample of 400 she has. Does she have a majority in the population? Well, what is a majority? A majority is a number, P, that's greater than 50%, or in other words, greater than 0.50. So the real test here is P is P cap, is it equal to is P cap equal to 0.50, or is P cap greater than 0.50? Okay, so that's what our job here is going to be. Okay, so now with this proportion, we can calculate a confidence interval. What is our confidence interval for what the real proportion that favor Christine Quinn is in the population? So how do we calculate our confidence interval? Well, 95% confidence interval for Pcap, right, is going to be equal to Pcap plus or minus 1.96, our sample size is big enough, obviously, times the standard error. Okay, and our standard error is going to be equal to, well, 0.75 p times 1 minus p over n, square root of the whole thing. That's going to be equal to the square root of 0.575 Alex, this came up a couple of times, I think. A couple of you asked me about it. I would say it's got to be greater than 50%, because the question was, does she have a majority, right? So anything greater than 50%, I'm going to test it against 50%. So we want 50% to be out of the confidence. In other words, if it turns out that our confidence interval, well, I'll get to it when we get to the very end and see what the number is. I'll discuss that. Okay. So, but let's not get distracted too much from what the actual problem is, because it's not likely. The only reason that would make a difference is if we got exactly 50% and as the lower end of the confidence interval. So that's not likely to happen anyway. So let's give it a shot. 0.575 times 0.425, I guess, right? Okay, over the sample size, which was 400. Okay, so let's calculate that. Let's see if I can't get it right this time, the first time. 0.575 times 0.425 equals this. Divided by, that looks right, divided by 400 equals this. And I'm going to take the square root of that. So it's 2.47, 0.0247. So our standard error is 0.0247. Okay, so now in order to find our confidence interval is Pcap plus or minus 1.96 times the standard error. Okay, so it's going to be 0.575 plus or minus 1.96 times 0.0247 or 2.5%. Okay, so let's see what we get. First, my margin of error. My margin of error is going to be 1.96 times 0.0247 equals almost 5%, right? 0.0484. So I got 57.575 plus or minus 0.0484. Okay, so if I subtract that from 50.575, I'm going to put this into memory, and I'm going to clear it. 75 minus memory recall is equal, it was a negative number. Somehow I got a negative number there. I'm not sure how. Let's put it in there. So if I'm right, the upper range was 0.623. And the lower range, how did I get a, yeah, I got a negative. I don't know how I did that, but that's okay. Doesn't matter. I'll just put a negative in this time. 0.575 minus, let me recall. Nope, I got that one. 0.575 plus, oops, 0.575 plus 4 memory equals 0.527. So we're 95% certain that her real population proportion is yeah, Anand even got it a little bit better than I did. Our real population proportion is between 52% and 62% of the population. Okay, is 50% the amount that you would need for a majority outside of that range, outside of that confidence interval? Well, it is outside of that confidence interval. So we're 95% sure that she has a majority of the voters in New York City. Didn't turn out that way, unfortunately, but that's the way cookie crumbles. She's got 52 at that time. That's probably, when I made this problem up, I think those might have been actually realistic numbers in polls. She was leading very early on in the polls. At any rate, so 52 to 63% is our 95% confidence interval for the true proportion. And since she would only need 50% to have a majority or more. So now, if the question was, does she have 50% or more of the population? Well, then you'd want her to, you want Pcap, you'd start off with Pcap is less than 0.50, and and the alternative hypothesis, H null, Pcap is equal. In other words, in this case, we wanted a majority. So we did Pcap is equal to 0.50, equal to or less than 0.5, oops, or less than 0.50. And the alternative hypothesis was Pcap was greater than 0.50. That would be a test of, does she have a majority, more than 50%? Had we just asked, does she have 50% or more, then Pcap would have been null. The null hypothesis would have been Pcap is less than 50%, right? And P alt is equal to or greater than 50%, right? A little bit of a mind bender, but you get the idea. In other words, you're starting out with the null hypothesis. Sometimes you want to start out with the alternative hypothesis, what you're trying to prove to set up the null hypothesis. However, the null hypothesis is always the default version, the equality. Okay, there's all, actually, I should have had the equality in. I should have had the equality. Should I have had the equality in here? I don't think it matters. Usually it contains the equality. Okay, I thought H null is greater than or, yeah, you could do it that way. Yes, H null is Pcap. Well, let me think about this. H null. No, you want to. That's Anand. You want to be able to if she has more than 50% of the population, 50% of the voters, you want to be able to reject the null hypothesis. So your null hypothesis would be that she doesn't have 50%. That they, in other words, you want to prove that she has more than 50%. Although, to tell you the truth, usually you put the equality in the null hypothesis. I think it'll work both ways, to be honest with you. In this particular case, numerically, you almost always have the equality in the null part. But the part you're trying to prove, whatever you're trying to prove, is what the alternative is, because you're trying to prove that you can reject the null hypothesis. The null hypothesis being that there's no difference, or she doesn't have a majority, and so on and so forth. So in this problem, it would have been that she was equal to or less, that the null hypothesis is that her proportion was Pcap is equal to or less than, right? The equality is in there, equal to or less than 50%. And our alternative hypothesis is that she has greater than 50%. So once we see this this standard deviate confidence interval, we can reject the idea that she's equal to or less than 50% because it's outside of the confidence interval. Now, if you really wanted to be tricky, what about a t-test here? What would t be here? T would be Pcap minus P over the standard error. Okay, so T would be equal to, let's see, Pcap was 0.575 minus P 0.50 over the standard error, which was, what was the standard error here? It was 0.02, 0.025, let's say. Okay, so T would be equal to 0.75 divided by 0.025. Okay, so T would be equal to a big number, right? Like 30 or something like that. That seem likely? That doesn't seem too likely. Standard error is that 0.0845. No, that's the margin of error. So we're only looking for, down here, we're only looking for the standard error. Oh, I'm sorry. You're right. It's 0.075, not point. So it's 3, right? Again, 0.075. 0.7575 minus 0.50 is 0.075 divided by the standard error. Remember, the formula for t is the difference in the two proportions or the two means divided by the standard error that you calculate. This is the two proportions. This is the standard error. We multiplied it by 1.96 to get 0.04, which was the margin of error. But here we're using 0.025. So t is equal to 3. So now this is a proportion. What does t have to exceed in order for us to reject the null hypothesis? How many standard errors apart do these two proportions or means have to be in order to reject the null hypothesis? Remember, it's a proportion now, a big sample size, so we're willing to accept as our critical value of t 1.96, the same thing we would use for z. So since these are three standard errors apart, we don't even have to go to the t-table because it's a big sample and it's a proportion that we're working with. So we know if it's over 1.96, we can reject the null hypothesis. This is the same thing as what we did with our confidence interval. In both cases, we get the same result. Okay, so the next question that we were talking about was to let's see, number 6. That was number 6 we went through. Okay, I lost the question. Should I have used 1.64 because it's a one-sided test? That's a good question. Technically, yes. You could have used 1.64. Well, hang on a second. Yeah, that's a tough one. Yes, since we set it up this way with our hypotheses, you could have used a 1.96, 1.64 as a single-sided hypothesis because we set it up in our null hypothesis as a one-sided test, right? So all 5% error could be on one side of the distribution. However, although going into this, we didn't know if she had more than 50% or less than 50%. Right? So I would have probably kept this a two-sided hypothesis anyway. Okay, so these proportions, especially like when it's structured like this election thing, greater than a certain majority and stuff like that. Just because the result was greater than that going in ahead of time, we didn't know if she was going to have more than 50% or less than 50% when the sample was taken. So if we had set up the null hypothesis before we started, we would probably be asking, is she different than 50%? And then let the data tell us whether she was greater or less than. So we might have started it out as Pcap is equal to 50% and P as the null, and alternate is Pcap less than or greater than, not equal to 50%. So yeah, it's kind of a funky problem to apply that to. Now I wouldn't worry about it too much. If I would have stuck with 1.96, I don't think anybody would have criticized you for using a more conservative two-tailed approach. Okay, so I lost track of what the other problem was.